Hey guys, welcome back to my YouTube channel. It's 2022. You want to hit that subscribe button and turn on your post notifications so you know every time I post. Well, hello there. Welcome back to my YouTube channel. So today we'll be going through VSERP theory. And VSERP stands for valence shell electron repulsion electron pair repulsion and theory goes at the end. So that's what VSERP theory speaks about, and in order to understand this you'll have to be familiar with Lewis structures. And what exactly are Lewis structures? Lewis structure basically shows you the valence shell makeup of, say, a compound or atoms itself. So let's take the simplest atom that we know right now, which would be hydrogen, and let's say we form a hydrogen molecule or H2 molecule, which is diatomic. Alright, so in this molecule, that hydrogen has one valence electron, and thus in a covalent bond between two hydrogen atoms you'll have these two sharing their electrons with each other in order to basically achieve the noble gas electronic configuration. So basically that means that all the outer electron or outer shells are filled, and thus the atom itself is stable. So as I said, you need to be a bit familiar with Lewis structures, and to be familiar with those we'll have to take a look at them for a bit. So let's look at barium or boron tetrafluoride, BF4. Right, quite easy. Now if we draw the atomic diagram for boron has the atomic number 5. Oops, so I'll be drawing this real shaky though. That's missile. So that's 2, 4, and 5. So it has 3 outer electrons, and by Hund's rule you know that we put them on singly first before we pair them, that them being the electrons. So now we'll have, and BF4 should have a negative charge. Show you why later. And fluorine, if we draw the atomic diagram for fluorine, and maybe I should change the color here, let's choose yellow. So if I draw the atomic diagram for fluorine, you know that fluorine has 7 valence electrons, right? And thus we have a space right here to accommodate another electron, while this boron atom has space here, 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 and basically the space to accommodate 2 electrons there. So if we were supposed to draw the Lewis structure for boron tetrafluoride, then what you'll find is we'll draw the boron atom and indicate the valence electrons available, which we know would be 3, and we have a space to accommodate 2 there. And if we attach 4 fluorine atoms to it, we'll have to deal with 3 first. And let me go back to the yellow. So F basically, and I'll represent these with dots, right? That would amount to 7, and the bonded pair here would make it 8. So that's what we call bonded pairs, while these here are what we call lone pairs. So lone pairs of electrons, while these would be bonded pairs. I guess this is quite easy to see. So we'll do the same with the other unbonded electrons from boron. So yeah, and I'm complete. Now it's supposed to be 4 fluorine atoms, and if we put these in here, this would be a fluoride ion that would be bonded. So that would mean that this would actually have an extra electron, because in order for a stable atom to become an ion, it either loses an electron or gains an electron. So for example, if you have a sodium atom which has, say, 11 electrons, its atomic mass is actually 23, has 11 electrons, and in order for this metal to become what we call a cation, it will lose 1 electron and have 10 electrons, which would make it like 8 valence electrons, where 8 electrons are on the outer shell and 2 on the inner shell, to actually make it 10 electrons in total. So with that said, this, because it loses an electron, you will now have a greater number of protons than electrons, and that would cause it to be positively charged. And in the case of anions, what will happen is the stable atom will gain an electron in the case of maybe most halogens. Yeah, so fluorine, for example, we have 1, 2. I really need to stop drawing these so wonky. 3, 4, 5, 6, 7, 8, 9, and here we go. In order for this fluorine atom to become a fluoride ion, it will gain an electron, maybe from the transfer of an electron from, say, a metal atom like sodium, right? And that would allow this fluorine atom to become negatively charged, because it now has 1 more electron than proton. Because remember, whenever these atoms aren't charged, they're neutral. That means that the number of protons is actually equal to the number of electrons. So by basic mathematics, you know, if you have, say, -4 for the negative charge and +4 for the positive charge, then these would cancel each other out to be 0. So that's basically how you want to think about it. But going back to these Lewis structures, that is why this BF4 would have a negative charge. So yeah, it's not that hard to think about. I hope you got it. So after doing that, whenever you're thinking about the Lewis structure, you want to think about how many, or the shape of the molecule, I should say, the molecular geometry. You want to think about the number of electrons that surround the central atom. So you need to identify an atom and use that as your central atom. And in this case, we have four bonded pairs surrounding the central atom. So this has 4 bonded electrons surrounding the central atom. So this would take a tetrahedral shape. And I guess I should have started from the simplest one first to show you how this would work. So we're going to redo this from linear going up to show you how these structures actually bend. So whenever we're doing this, we want to think about lone pair repulsions, bond pair repulsions, and lone pair bond pair repulsions. And intuitively, lone pair, I'll just write as LP, bonded pair, I'll write as BP, and yeah, that's all we're going to deal with now. So we want to think about this, or remember this concept, that lone pair repulsions are greater than lone pair bonded pair repulsions, and these are greater than the bonded pair repulsions. So that would mean that a lone pair would repel a lone pair more than how much a lone pair would repel a bonded pair, and bonded pairs repels themselves way less than, say, a lone pair would repel a bond pair, and a lone pair would repel another lone pair of electrons. So yeah, so for example, let's look at carbon dioxide. So carbon would be the central atom, and they would be double bonded to oxygen on this side, double bonded to another oxygen atom on this side. Now this would have a bond angle of 180 degrees because this is a linear structure. So it resembles a straight line almost, or I shouldn't say almost, but literally it represents a straight line, and the angle of a straight line is 180 degrees. So yeah, so this would make it linear. But how would we know that this is linear? So here we have bonded pairs here, bonded pairs here, right? So in each double bond, we have literally 2 electrons from each atom. But we can treat this as one bond if we're thinking about Lewis structure model. And the goal of this is to actually have these these atoms be as far away from each other as possible, having where it would have the maximum repulsion. So as far away from each other as possible to not interfere with each other. So you want to think about us having one circle here, and you attach another circle to this side, and you want to decide where would be the most appropriate place to put another circle in order to get it as far away from this one as possible, and that would be on the opposite side. So that's how we got that linear structure. Now, if we were supposed to add another atom to this structure here that is linear, what you'll find is they'll try to push themselves farther away from each other, and it would be like equidistance away from each other. So let's look at it. So we have another circle, and we add an atom to the structure. We add another atom to the structure, and if we add another atom to the structure, we'll need to push these further out from each other, right? So we'll end up with what we call a trigonal planar structure, basically a flat three-pointed structure. So looking a bit like this per se, and we say that this is trigonal planar. Let me move this around a bit, that looks a bit better. So this is trigonal planar. Now, if we were supposed to add another atom to this structure, we couldn't add it in between anywhere here, because then it would be a bit too difficult to have them being spread equidistances away from each other. So the next available space would either be at the top here, or at the bottom, So you need to think about this in 3 dimensions, and I hope I drew that a bit properly or better for you to understand. So we'd have to stick it on the top here or on the bottom there. Now, in a case where we'd stick it at the top, that would cause these 3 points here to be pushed downwards, and we'll end up with a pyramid shape per se. So something looking like this. And seeing that it's a 4-point pyramid, we'll call this structure tetrahedral. Now, the difference between, say, a tetrahedral structure and a trigonal bipyramidal is that this pyramid shape is caused by another atom, while in a trigonal bipyramidal structure, the pyramid shape is actually caused by a lone pair of electrons. So we can represent it like this. So this pyramid shape is caused by a lone pair of electrons, and this is our lone pair right here. And so this would be trigonal bipyramidal. Yeah. And for the tetrahedral structure, as in this case right here, this pyramidal structure was caused by the addition of an atom. So there is an extra electron pair surrounding the central atom, which I have labeled in yellow right here. So yeah, so those are the basic structures for the Lewis structures. So if we want to take a look at some examples, and we'll wrap this up and I'll place the organic compounds in part 2. So if we look at some examples, for example, boron trifluoride, which is BF3, we'll use boron as our central atom, and I'll just use circles to represent this because you don't really need anything else. You need to add 3 fluorines around it and have them spread as far away from each other. Let me change the color. As far away from each other as possible. So basically, push these out a bit more, and in that case you'll end up with boron being a central atom still, and maybe or let me not say maybe, definitely, you'll have the fluorines being away from each other. You'll have the fluorine atoms being away from each other, resembling the structure right here. And thus we have, if you actually look at this, it's easy to remember because a circle has degree 360, and if we divide 360 into 3 equal parts, then we would get 120 degrees. So the bond angle of something that is trigonal planar is 120 degrees. All right, so that would be, for example, boron trifluoride. If we look at another example for, let's say water. Water is a bit different. Water is what we call V-shaped or bent. So ideally, you'd have hydrogen being your central atom, or lies, oxygen being your central atom, because the formula for water is H2O, so you'd have 2 hydrogens. You would expect these to be linear, seeing that hydrogen would try to be, these bonded pairs here would try to be as far away from each other as possible, and that would constitute something that's 180 degrees. But oxygen has 2 lone pairs of electrons on the central atom here. So these lone pair LP, lone pair bond pair repulsions, are greater than the bonded pair repulsions. So in a case when compared to this lone pair and this bonded pair here, and this lone pair and bonded pair here, these 2 lone pairs have no problem coming closer to each other, because they definitely don't want these lone pair bond pairs to be close to each other, seeing that the repulsion between a lone pair and a bond pair would be greater than repulsion between bond pairs and another bond pair. Then you would have this water molecule being bent or V-shaped, because then these lone pairs will actually push these bond pairs down, and thus you'll get a structure looking like this. Right? So yeah, it's all bougie. So you just need to understand the 3-dimensional structures, and the bond angle for this would be 104.5 degrees. So yeah, I guess you can practice and it should be great for you. So in part 2, I'll go through the organic compounds, and we'll discuss hybridization again and see how the shapes of organic compounds are, how they come to be. So I hope you understood. Leave some questions in the comments, and remember to subscribe to my YouTube channel and hit that like button and share my content with a friend. Also, my socials are linked in the description below, so connect with me on Instagram, tag me, I'll of course reshare or repost. And until next time guys, bye.